Good morning.
Good morning.
Okay, so I'm running a little behind. I'll get notes up today or tomorrow and the assignments. We have, for this module, we've moved out of modules of computation. We're going to spend 3 weeks on different aspects of compilation. And the topics that are in there, you may not relate directly to compilation in your careers, but the things that you do during compilation show up in different places. So today we'll talk about lexing and parsing, and then the homeworks that are due. There's the homework 4, which is the Turing machine homework is due tonight. And then there'll be a lexing and parsing homework due Friday, and then another one Monday. And the one on Monday is going to be, no, I don't know. I might make it a 24-hour one, but I might release it earlier than that. Neither of those should be terribly difficult. This is historically a piece of the course that people do well in. It would help if I shared my screen, right? Okay, so we'll do, like I said, lexing and parsing. And what we're going to do is go back to the BNF grammars, because everything is based on BNF grammars, and look at them in a slightly different way. So let's see here. Outcomes as usual. Fix my typo. Okay, so why are we studying this? There's been a change in the way computer science is taught over the last 15 or 20 years. If you were taking a computer science degree in the 80s, let's say, you would almost certainly have a complete course on compilation. In my grad studies, I took 2 courses on compilation, one for single processor and one for parallel environments. But these days, there's so much software out there that helps you develop compilers that you'll almost certainly never design one from scratch. You almost certainly will not design your own programming language. Now, I could be wrong in that. There's a lot of special purpose programming languages that pop up all the time. You know, we all know about C and C++ and Fortran and MATLAB and Python and Java and Ada, and those cover most of the commercial world. But you know, there's some 5,000 plus computer languages out there, and a lot of them are just special purpose languages that got built to do a very specific job. So you probably won't build your own programming language, so that's not the point of this. However, you should understand what the compilation process is. If you're going to be a software engineer, it's helpful for you to know what the compiler is doing. Sometimes your coding decisions could actually be affected by compiler behaviors. If you know that a classic example is when you have 2-dimensional matrices, how are they stored in memory? Different systems store them differently. Some store them in column order, and some store them in row order, one row after the other, or one column after the other. And if you do your nested loop the wrong way, then you pay a huge penalty in memory access time. So it's good to know that your compiler probably has a setting where you can make it optimize the loop order. And that's a standard optimization, to change the sequencing of the loops. You know, if you have one loop inside the other and you're hitting every element in a 2-dimensional array, it probably doesn't matter the sequence in which you're hitting those. So it's good to know. Plus, it's also good to know how a compiler works in the sense of how it breaks down your code, because you might think you've got some great ironclad code, and then it turns out by the time the compiler is done with it, you've got potential race conditions. You've got situations where your code could leave your program in an unknown state, which is a robustness issue and a security issue. Understanding how compilers work helps. And even though you probably won't be designing a programming language, you will almost certainly be parsing data at some point in your academic or professional career. And the same techniques for parsing data, it's the same technique for compiling a program, because to the computer, there's no difference. It is helpful for you to remember that the code that you write, this beautiful code that you spent all this time over, cannot be executed. It has to be executed at the machine code level. What's machine code level mean? Well, you've seen where people design chips and then they advertise, oh, we've got the latest chip. I don't even know what the latest chips are. What is it, Intel Inside? And they talk about how great it is that they've got this particular chip, or this particular, now they have 2, 4, 8 chips inside a single machine. When those chips are built, they're built with a very specific set of machine instructions. They're hard-coded, they can't be changed. And the machine code instructions are just a series of zeros and ones. And I think those of you guys that took operating systems, hopefully you studied this fetch, execute, store process that operating systems go through. They fetch a machine instruction. It has to be the zeros and ones that the chip understands. And then they resolve some of the memory references, and then they actually perform the computation, and then they store the result. Well, that's the level the machine is operating at. So when you're writing in Java, or if you're writing in Python or any other high-level programming language, there has to be some kind of a transition. And that transition is taking your code down into the machine code. And because what you're writing is usually a large number of operations, and the machine code can only do very stupid, simple, specific operations, like multiply by 2 or compare 2 numbers. The one line of code that you wrote often gets broken up into multiple machine instructions. So you think you wrote one line of code, and you think, oh great, that line of code gets executed, and then the next one. What if half of your code gets executed, and then the chip goes to somebody else, goes to some other process? Remember the way that these machines work. There's always, on a modern on a modern Windows machine, there's always 50 or so processes running at any point in time. Well, how do they do that? Each of them gets a chip for a short period of time. So your process gets the chip for a short period of time. It performs a piece of a computation, and then it loses the chip to another process. And then the question is, what happens if something wonky happens to your data while your program is waiting for its turn to get the chip back? Could that happen? What happens if you write several lines of code and you wrote them as 1, 2, 3, but the computer doesn't execute them 1, 2, 3. It executes them 2, 3, 1. That kind of stuff can happen. And the idea behind a program optimization is the compiler is allowed to manipulate the sequence of execution that you did, as long as it doesn't theoretically change the input-output behavior. But that doesn't mean that always works perfectly. As we know, machines don't always work the way we think they're going to work. And when you get into the nowadays the modern world of highly internet, highly networked situations, you've got all kinds of opportunities for mischief. All right, the overview, the different parts of the process. Now, different authors will list these differently. They're basically all there. Sometimes different authors will lump some of these together or break some out. It depends on what that specific author wants to emphasize. But the basic process is this. There's something called lexical analysis. Now, I'm going to start to use the word tokens quite a bit. When you write a line of code, then each string inside that line of code, which is in itself a string, but each string that is separated by white space, let's say, is just going to be taken in and called a token. And what the lexical analysis does is it determines the roles of the token that it just took in. And you're used to this. You had to do this in 8th or 9th grade somewhere along the lines, right? They would say, what'd you have to do? Draw a fish diagram for the sentence? You've got a noun, a verb, a noun phrase, and the noun phrase breaks up into, what is that, an article, and a noun. Or you can say, and then you say, oh, okay, this is a noun phrase, this is a verb phrase, this is a noun phrase, and then each of those phrases gets broken down some more. So you've done this with natural language, and the same thing has to happen. The same thing has to happen with programming statements. What is this thing? What is this thing? Right? The computer always asks, what is this thing? And then if I put them all together, did I get something that's in the language or not? So if I say, what is this thing? Oh, okay, it's not a keyword. If it's not a keyword and it's not an operator, I'm going to say it's a variable. Usually, by the way, they use the term identifier. I'll use those interchangeably. Oh, okay, so we have identifier. Oh, that's an assignment operator. Identifier, assignment operator. Oh, that's a number. So this thing gets parsed, and that's an end of line marker. So this thing will get parsed into, gosh, if I could type. Identifier, assignment operator, number. So that's what's happening with lexing. It's determining the roles that the different tokens play. And we'll talk about why that is a good idea in a couple minutes. Once the lexing is done, then we can do parsing, syntactical analysis, parsing the sentence, parsing the statement. Basically, it's answering the question we've been answering for the first, so far in this course, using stack machines and finite state machines, and asking the question, is this statement a legal statement in the language? If the language is Java, is that a legal Java statement? If it's Python, is it a legal Python statement? And they're going to use exactly the same techniques that we learned in the stack machine in order to do that. Once the parsing is done, oh, and by the way, how do you know if you've got, it's kind of a recursive structure, okay? So each, say, variable or identifier that you list is a string, but that's going to occur in a statement like an assignment statement or a while loop or an if then else. And each one of those is also a string. Oh, and then you have statement after statement after statement, which is a program, that's also a string. So your program can be thought of as one big long string. And inside that one big long string are shorter strings that represent program statements. And inside those program statements are shorter strings that represent variables and operators and values like numerical values or Boolean values or string values. That's the syntactical analysis. You have to do the lexical analysis first to make that easier. We'll talk about why in just a second. After that, we go into semantic analysis. Now in semantic analysis, that's where you're looking not so much as the structure, but you're looking in a very limited way at the meaning. Now, we just proved, or at least did a proof sketch with Turing machines that said you cannot build software that looks at another piece of software and then says anything of real significance about its meaning. Will it halt? Is it a virus? That kind of thing is not doable. However, you can do some simplistic semantic analysis. You can do some simplistic stuff. What you're doing there is type checking. If you've ever got a type check error, that was not a syntactic problem, that was a semantic problem. Some programming languages require that you initialize variables before you use them, and if you don't, then you'll get a error that says, you know, use variable not initialized prior to first use or something like that. That's a semantic issue. So once those things happen, we've got the machine says, okay, I know what the tokens are. These are all legal strings. The program seems to play together, at least from a type checking standpoint. We can do more sophisticated semantic analysis, by the way, and we'll talk about that in a week. Then we go into optimizations. And here's where your program really gets ripped apart. It gets ripped apart and it gets represented into a different format, typically called intermediate representations. And they're called intermediate representations because the user never sees them and the machine code never sees them. They're intermediate. And then what happens is there's a standard set of optimizations that can occur to try to improve either the efficiency of your program in terms of computation cycles, or the efficiency of your program in terms of memory fetches, or the efficiency of your program in terms of the maximum amount of memory that you need to use at any point in time. By now, your program is wholly unrecognizable. Once that occurs, then the optimized code in its intermediate representation form is translated into machine code instructions. So that's the code generation. And now where they're actually using the instructions that come with the chip. And from there, we have assembly. Now, again, I said authors use things, authors will frame these things differently. Some people chunk code generation and assembly together, but basically the code generation is machine code instruction. Often your program is still in pieces. And so what the assembly is doing is taking the pieces and putting them together. And particularly what's happening, at some point you're gonna have some kind of, you need memory references. And so the assembly is connecting the parts using memory references, not direct references like pointers, but they always use offsets because you never know where the code is going to be stored in memory when you start running it. So these are the basic tools. It's basically the first part is, hey, is this a legal program? And it is, did it parse? And then the second part is, are the type checking things correct? Okay, let's optimize this thing. And then the last part is, okay, let's actually create the machine code. If you are adept at using a compiler, you can turn on and off the aggressiveness of the compiler in terms of optimizations. You can have it flag certain things or ignore certain things. So becoming familiar with the compiler that you're using becomes a skill over time. And did any of you guys ever use a makefile? You might have to use one in your professional career. So instead of having a GUI, what you see is what you get tool like Eclipse, we used to always compile code using something called a makefile. And the makefile was basically a set of compiler instructions that said, here's what to compile, here's how to compile it. Well, what the programs like Eclipse are doing is they're giving you a graphical version of a makefile. And so when you are aware of what options your tools give you, you can control your compilation more closely. So if you're getting some issues from the compiler and it's not really an issue, it's just a way the compiler was built, you may have the opportunity to turn that off and your code will be fine as long as you did your code correctly and your analysis is correct. These are good things to know. Okay, lexical analysis. And I've already done some of this, so we're going to go through this a little bit fast. But basically, it's replacing the string in the program. Each string is a token, and it's replacing what you wrote with tokens. Now, that doesn't mean your program's destroyed. It has to keep a copy, obviously, so that it can actually rewrite your code. It can't keep things in this bland, anonymous way, right? I'm writing var here for shorter, but often you'll see identifier in this bland way. Right, if everything was just var or identifier, you know, you wouldn't know X from Y or Z. But that's what's happening. The lexer is tokenizing your strings, tokenizing your program, and then determining the role of each token. Now, why? Why did they do that? Well, programming languages are defined by their BNF grammars. And if you wanted to try to provide a BNF grammar for every, if I gave you this as an assignment, create a BNF grammar for every legal variable name. Where I want you to be able to explicitly represent in your grammar all possible variable names. The grammar would be huge, right? It would be hundreds of thousands or maybe millions of rules big. So what do? We take every variable name and just say, oh, that's a var or an identifier, depending on what author you're looking at. Now, instead of having hundreds of thousands of rules, I have one. And instead of having, how many math operators? This is right from the link here. I've got what, 1, 2, 3, 4, 5, 6, 7, 8, 9. There might be more. I can't see it back there. Yeah, 10, 11, 12. Okay, so there's 12 assignment operators here listed for Java. Rather than having 12 rules, one for each unique one, I can have one rule for assignment operator. So that's why the lexing is done. It's to reduce the number of rules that you have to deal with. This is worth showing. Will this let me? So here's Java BNF. There's multiple versions out there. They're all pretty similar. And you can start with the top level. What's a program? It's a package declaration, import declaration, type declarations. Okay, then we go down and look at what those things are, and they're going to be broken down and broken down and broken down. And type declarations are class declarations and interface declarations. But that sounds like a Java program, right? What's a class declaration? Well, class modifiers, class, identifier, super. Oh, okay. What are these modifiers? Public, private, static. The word class is a terminal. Identifier, that's the class name. And then super. Oh, what's super? Extends class type. So you can work from the BNF rules forward and derive your Java program. Now, by working forward, I mean moving from left to right. If you go down, 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 primitive type can either be a primitive type or a reference type. Primitive type is either a numeric type or a Boolean. Numeric type is either integral or floating point. Floating point is float or double. Integral, byte, short, int, long, char. So you get the idea. The BNF rules exist, and they use the BNF rules, the compiler does, exactly the same way that we did it when we were saying, is this string in a language for a stack machine, like we did 2 weeks ago. Now, because there's so many more rules, it's not done by hand, or we'll talk about that. But it's the exact same idea. And again, anything that you're doing here for a programming language, you could do for data. If you have to parse a database, you can create the BNF rules for the legal forms of the data and then build a parser for it. And you almost certainly wouldn't build that parser by hand. There's software that's out there. Okay, then once we do the lexing, then we get into the syntactical analysis, the parsing, and again, the BNF rules are used, and there's two ways to do it. There's something called the top-down method. You begin with the start symbol, and then you use the rules to derive the string. This is the manner that we used in the simple languages for finite state machines and for stack machines, right? I would ask you, hey, draw the machine for this, and then write the grammar and derive the string. Write the grammar, draw the machine, derive the string. That was top down. You're using the rules from left to right. The form of that comes out most popular is called recursive descent parsing, and it's called recursive descent parsing because it recursively calls things. So for example, you start out saying, derive the program. Oh, okay, in order to derive the program, I'm gonna have to derive a statement. So you've got modules in a recursive descent parser that say, is this a correct statement? Now think about it, there's a couple of different forms of correct statements. Is this a correct assignment statement? That's pretty straightforward. But what about, is this a correct if then else statement? I've got some kind of a test here. Okay, so how many lines of code is that? This stuff here. How many lines of code is that? Let me move it around and make it harder for you to count. 6. Good. Anybody else? And you're counting it as 1, 2, 3, 4. I'm getting 5. Anybody else?
Do you not count the last bracket at the bottom?
That's a good question. So if we count it, it's 6. If not, we count it 5. How many people got 1? How many people say it's 1 line of code? Or 1 statement, I should say. All these answers are correct. It is 1 line of code. It's 1 line of code that contains other lines of code. And that's why the recursive descent parser is a recursive descent parser. Because if you call off the function that says, hey, tell me if this is a correct if-then-else block, that's considered 1 line of code. But inside that if-then-else block, it contains assignment statements. So the if-then-else block has to call assignment statements, the assignment statement recognizer. And of course, I'm going to screw this up, I think. Let's see. There we go. Oh, whoops. Gosh darn it. In order to recognize this, I have to call my if-then-else recognizer. So I've already called it once. And inside I've got, now I've got to call it again. So my if-then-else recognizer, as part of recognizing if the outer if-then-else is correct, has to call itself on the inner if-then-else. That's recursion. So recursive descent parser is going through and trying to derive the string using this mechanism. Most parsers don't use that. Most parsers do the opposite. They use a bottom-up method. They actually start with the string, which makes sense because your program is a string. They actually start with the string. So, and they go backwards. They use the BNF rules backwards and try to produce the start symbol. Now think about if that makes sense to you. If I can start with the start symbol and derive the string, and I produce a sequence of steps, then can't I just do those steps backwards, starting with the string and ending with the start symbol? Are these rules not reversible? So here's my DNF. Oops. And if I said this was rule 1, 2, 3, 4, 5. This is where I like whiteboards. And then what's a good string here? AAB. Okay. Can I derive that string? Sure. I go S goes to A, goes to AA, goes to AAA, goes to AAB, goes to AAB. And the rules that I used, gosh darn, stop doing that, are rule 1, 2, 2. This seems wrong.
I think you missed a step.
I think I screwed something up, yeah. And, oh, I think I have to do B, B, A, B, and then I'm going to use rule 5. Okay. Oops. All right, so that's what it is. I'm off by 1 because this should be, in order to get here, I used rule 1. There we go. I used rule 1 to get the capital A. I used rule 2 to get the AA, rule 2 to get the AAA, rule 3 to get the AAB, rule 4 to get the AABB, rule 5, right? Now, if I started with AAB and used those rules backwards, working from right to left instead of left to right, would I or would I not end up with the start symbol? It's a reversible process. Now, why? Why in God's name would you do this backwards? Well, here's why. If I currently have an A and I want to go forward, how many options do I have? 2. If I currently have a capital B and I want to go backwards, how many options do I have? 1. So what you're doing is you're reducing the number of options you have to deal with at any point in time. Now you guys, and I think most of you have already taken CS315, you know what a tree structure is. You know that if you're going down a tree, you have options as to which path you can take. But if you're going up a tree, you don't have any options, right? There's only one parent per child in the tree for most normal trees. So what the bottom-up parsing is doing is reducing the number of options that you have to deal with at any point in time. So that's what's happening. It's called shift reduce parsing. It actually uses a stack. And what you do is you keep piling on symbols onto the stack until you find a rule that you can use backwards. And if you'll notice, most of the rules, when you use them backwards, remember when you go forwards, you create terminals. When you go backwards, you're going to reduce the terminals and reduce the non-terminals, so you're going to reduce the size of the string. So if I use rule 2 backwards, in this simple case, I go from 2 symbols to 1 symbol. And so what's going to happen is you've got stuff on the stack, but then you can reduce it. For example, if I have that on the stack, I can reduce that to one thing on the stack. Is this not an assignment statement? Yes, assuming I put the right semicolon at the end. But yes, that's an assignment statement. So once I see that pattern, what I can do is reduce the stack and just replace it with, oh, I've seen an assignment statement. So this is why it's called shift reduce parsing. You're going to shift things onto the stack and then reduce. And we're going to go through a detailed example probably on Wednesday. Now, in order for this to work, there's a way that we can visualize this called parse trees. And here's the problem. Again, we've got another problem, right? The problem is, and I don't have the problem in this grammar. In this grammar, in order to produce the string AAAB, in order to derive that string AAAB, I've only got one possible sequence of rules to follow that will do that. But you guys have created grammars, and I've shown you grammars in the past where for a single string, you have multiple derivations. You can choose what rules you want to pick. A simple case like that would be the classic So what I'm going to get here is by creating the, by using rules 6 and 7, is I'm going to get that. And once I get here, can't I choose which A I want to turn into a B at any point in time? So I could do the first A, or I could do the fourth A, or I could do the last B. That could be my next step. And they were all correct. There's multiple derivations for a particular string. And as we know, we don't like to give computers choices. It wastes time. So how can we get rid of this notion of, gosh, there's so many possible ways to do this? Instead of thinking of it as a derivation, which is linear, we're going to think of it as a tree structure. And so we have this thing called a parse tree. And I'm going to give you more examples of this on Wednesday. But you start out with a parse tree by saying, oh, okay, the root, by the way, let's all remember what a tree is. A tree is a graphical structure where there are nodes. There is exactly one node called a root. Every other node is involved in a parent-child relationship. I'm sorry, the root is also involved in a parent-child relationship, but the nodes are involved in a parent-child relationship where the parent may have more than one children, but each child may only have one parent. So if you look, node S has node C, S is the parent, C is the child. Node C actually has 3 children, A, C, B. That's just the structure of a tree, not just a parse tree, all trees. There is exactly one node that has no parent, that's called the root of the tree. And then there are nodes that have no children, and those are called the leaves of the tree. And just to torture the analogy a little bit more, once you go down a particular path, if it has more than one node, that's typically called a branch of the tree. Parse trees show you a graphical version of how the rules can be used to construct a string in tree form. The root is the start symbol. Now, if you look at rule 1, start symbol gets replaced with a C. So, okay, start symbol gets replaced with a C. That's the parent-child relationship. But C gets replaced with ACB. So if you look at here at C, it gets replaced with an A and a C and a B. They all come off separate branches of the tree. You cannot clump them together. You don't say C goes to ACB where ACB is all on one node. Each individual non-terminal and terminal are dedicated to their own node. And then A goes to A, B goes to B. This C, we're going to branch out again, A, C, B, because that's the rule, using rule 2. And then for this C, I'm going to use rule 3, which is it just goes to A and B, but there's no C in the middle. And then the A goes to A, and the A goes to A, and the B goes to B, and the B goes to B. Now, if we did this on a derivation, let's see, if I wanted to derive string A, B, what do? I have S, goes to, I'm not going to put the rule numbers, goes to C, goes to ACB, goes to AACBB, goes to AAABBB, and then I have a choice. I can do this, or I'm not going to do them all, or right? I have choices. So I have many derivations. But look at this parse tree. Try and make another parse tree for that string. You can't. You can't. And boy, is that a good thing for a compiler. No choices. No choices at all. Okay, there has to be questions here. Okay, I'm going to come up with one more thing, and then we'll call it a day. Now, I could create a grammar, and I've done it here. I could create a grammar that allows multiple parse trees. And if you have a grammar that's called that allows multiple parse trees, that's called an ambiguous grammar. This definition is important. An ambiguous grammar is one that will allow multiple parse trees for the same string. And that's bad because we never like to give our parsers the option of choice. And you can actually create infinite loops inside of parsers if you have ambiguous grammars, because you may have basically infinite recursion. So an ambiguous grammar, by definition, is where you can create multiple parse trees for at least one string. And I'm going to ask you about this on your homework. Is this grammar ambiguous? Why? Is this grammar ambiguous? Why? You know. And that's the answer. Now, what does that mean for at least one string? Well, what if I gave you a grammar and a string, and for that particular string, you could only create one syntax tree or one parse tree? And then I said, is this grammar ambiguous? If you said, no, the grammar is not ambiguous because for the string you gave me, there's only one parse tree. There's a problem with that answer. What's the problem with that answer? You guys are as tired as I am this morning.
Wait, can you repeat that again?
Sure. If I gave you a grammar and a string, and I said, draw the parse tree for this string, and you found you could draw only one parse tree for that string. And then I said, is this grammar ambiguous? And your answer would be no, because I could only draw one parse tree for that one string that you gave me. Is that a good answer?
We have to test other strings.
Yeah, that's the thing, right. And that's the thing that students will miss on that question. Look at the definition. Use your experience in writing requirements to read that definition. If there is at least one string in the language, then it's ambiguous. Which means even if there's only one string in the language, it's ambiguous. So it's not about the string that I gave you, it's about all strings. Now, how could you prove a grammar is ambiguous? An existence proof. Come up with a string that has multiple parse trees. So I'm proving to you that this grammar over here is ambiguous because for the string AAABBB, and I just added some useless crap to it, by the way, to make it ambiguous. You know, good old non-terminal D out here is doing nobody any good. But now I've got the original parse tree that I showed you on the previous page, and then I've got a new parse tree that has D in it. So I've got two parse trees for the same string. That's an ambiguous grammar. Okay, we'll look at more parse tree examples, and then I'm going to walk through a shift reduce parsing example on Wednesday. And I'll have your notes up. Hopefully tonight, it might be tomorrow morning. And all these questions that you're not asking now, you can put in the discussion section. Fair enough?
Yeah.
Yes, sir.
Good to see you guys. Good day.
Thank you, Professor.